Hello chemists, this is Ms. Placino and you are watching lesson 7.3 on phase changes. Today we're going to talk about what happens to the particles of a substance as it undergoes a phase change. Goals for today's lesson. You should recall the 6 common phase changes. Those are the ones that happen between solids, liquids, and gases. We did discuss them earlier this school year. It's okay if you've forgotten, we will review. You're going to be able to use table H in your reference table to relate atmospheric pressure, vapor pressure, and boiling point. We'll also be looking at heating and cooling curves. You should be able to interpret those, as well as interpret phase diagrams. So today's lesson is pretty heavily steeped in getting information from a diagram or a chart and doing something useful with it. So this is a really important skill. Let's go ahead and get started. We'll start off by talking about vapor pressure. Vapor pressure is simply the pressure exerted by a vapor when it is in equilibrium with a liquid phase at a given temperature. So let's kind of break that down into what it means. In these 2 Erlenmeyer flasks, this is kind of a start and then at equilibrium. So we start off by putting some liquid, most likely water, in an Erlenmeyer flask, and we cork it. This prevents anything from entering or leaving the flask. Initially, when we do that, at whatever temperature we pick, even if it's at room temperature, some of those liquid particles are going to have enough energy to leave the liquid phase and become a vapor. At equilibrium, the total number of gas particles, or vapor particles, depending on however you'd like to look at it, is going to remain constant. The total number of liquid particles at equilibrium also remains constant. But there's going to be motion. Some of those particles that are in the gas phase will condense and become a liquid. And at the same rate that that's occurring, and at the same time, some of the liquid particles will evaporate and become a gas. It just takes time to kind of let a system equilibrate. And that just means that these 2 opposing processes, evaporation and condensation, are occurring at the same rate. When something is volatile, that means it has a high vapor pressure. You've probably worked with those little alcohol wipes before. They're in that little foil pack. You know when you rip that open, almost immediately you get hit with that scent of rubbing alcohol. That's because rubbing alcohol is relatively volatile. It has a high vapor pressure. That means that there are lots of particles in the gas phase. Other substances get classified as non-volatile. They have a low vapor pressure. So you have few particles in the gaseous phase. If we try to relate these ideas of volatility and vapor pressure back to boiling point and intramolecular forces, what do you think the relationship might be? If you have a volatile substance, so something when it reaches vapor pressure, it equilibrates, has tons and tons of particles in the gas phase, what must be true about its boiling point and intermolecular force strength? Let's say you have lots of particles that are already in the gas phase at the temperature we picked, so it probably has fairly weak intermolecular forces. Particles are not attracted enough to each other to stay in the gas phase, so they're able to evaporate more easily. If they evaporate more easily because of those weak intermolecular forces, we should see a lower boiling point. If we compare that to something that is non-volatile, so there are very few particles in the gas phase, we must have, comparatively speaking, strong intermolecular forces. There's enough attraction between the liquid molecules to keep the molecules as liquid. We would expect to see a high boiling point. Got to put more energy in to let those molecules move away from each other. So really make that connection between the term volatile with high vapor pressure, lots of particles in the gas phase when equilibrium is established, weak intermolecular forces, low boiling point. And the exact opposite holds true for our non-volatiles. Low vapor pressure, very few particles in the gas phase. As a result, you tend to have high intermolecular forces and a high boiling point. Let's get into interpreting some vapor pressure curves. All right, you've got a table in your reference table, table H, that looks pretty similar to what we've got on the screen here. You see temperature across the x-axis, pressure on the y. This chart is showing pressure in terms of torr. Yours is in terms of kPa. Those are just two different units for pressure. And in both cases, that dotted line, of course, black on your table, red in mine, is representing atmospheric pressure. So I'm just going to call this normal pressure. This is the pressure that we're used to experiencing every day. Boiling is going to occur when the vapor pressure is equal to the atmospheric pressure. So if you got like your pot of boiling water, or pot of water, you put your liquid in there, we have atmospheric pressure pushing down on it. Capital P. In order to boil, your vapor pressure has to be equal to the atmospheric pressure. So I'd like you to think about it this way. We're going to imagine that you are a liquid molecule. You are sitting, and you've got a friend taking his or her weight and pushing on your shoulders down with all of their weight. Them pushing is the atmospheric pressure. If they're pushing really hard and using every single pound of their body weight, it's going to be hard or easy for you to stand up. Probably pretty challenging compared to how it usually is. That represents a high atmospheric pressure, putting a lot of pressure on the vapor and on the liquid, so it's going to be difficult to boil. Now imagine your friend is just resting their hands on your shoulder, really not like using any force whatsoever. It's going to be pretty easy to stand up. That is low atmospheric pressure, and the amount of energy required for you to stand is representative of the boiling point. So at 1 atmosphere pressure, water has a boiling point of 100 degrees Celsius. Common misconception is something has to be hot to boil. It's not necessarily true. Just the vapor pressure and the atmospheric pressure have to be equal. So if we knock down the atmospheric pressure a lot, say we go down to 200 torr, that's not like a quarter of what the usual pressure is, we're going to see a dramatic change in the boiling point of water. It's a little bit less than 70 degrees in that case. If you've ever seen high altitude cooking instructions, it's because of this change. Water boils at a lower temperature, therefore cooking times are going to be different. Sure, the water might boil faster, but it's going to cook a lot more slowly, like if you're making pasta, for example, and water that's at about 70 degrees Celsius than it would at 100 degrees Celsius. So that's what high altitude cooking instructions are all about. You got some practice problems helping you kind of learn how to use table H. Definitely worth checking out. Ooh, sorry about that. All right, the next graph that I'd like to look at are heating and cooling curves. Do I have a heating or a cooling curve here? Now, hopefully you see the term heat absorbed. Makes you think you're putting energy into the system. So that sounds like something heating up. And sure enough, the general trend of our plot here is increasing in temperature. This is representing how temperature changes as heat is absorbed. So it turns out we're working with water here. So if we look at water somewhere between -50 and 0 degrees Celsius, what phase of matter is it going to be in? Yeah, of course, it's going to be a solid. We'll have ice at those temperatures. The next slanted line, we've got 0 to 100 degrees Celsius. We'll assume we're at 1 atmosphere of pressure. Yeah, we're working with liquid water. And if you can get water up over 100 degrees Celsius, it is going to be in the gas phase. No surprises there, hopefully. The interesting part of this chart has to do with these two flat lines. Here, we're putting energy into the system. Heat is being absorbed. But no temperature change is occurring. What's happening at this first star, the one in between solid and liquid? Yeah, here we're undergoing a phase change. Melting is occurring. We call this the heat of fusion. Don't worry too much about that symbol. We don't need it right at this point in time, but it will come up a little bit later in the school year. What about that line? the long one in between liquid and gas. Yeah, that's vaporization. What requires more energy? Melting solid ice or vaporizing liquid water? Vaporization requires a lot more energy. Go from, what's that, maybe 900 up to about 3,200 kilojoules had to be absorbed to vaporize our sample completely. Maybe we've got 100 to 450 or something. Far fewer kilojoules of energy were absorbed to melt the substance. You can tell based on the length of those lines. If we think about what's happening on the molecular level, we know our solid, really rigid, everything's close together. When we melt, we end up with a particle still pretty close together, but with more flexibility to move. And finally, with our gas, they're really spread out. Why does that second change, going from liquid to gas, require so much more energy than going from solid to liquid? I'll give you a hint. Think about IMFs. What's happening with our intermolecular forces? Well, as we go from a solid to a liquid, IMFs are just kind of compromised. They're still pretty strong. Still lots of attraction between the particles of the substance. There's just more flexibility, more movement, I should say, between molecules. What happened to IMFs as you go from a liquid to a gas? Yeah, they basically have to be destroyed. You need to put in enough energy to separate the molecules away from each other so that they can spread out and behave as a gas. It takes far more energy in most cases to destroy those intermolecular forces as we go from liquid to gas than it does just to compromise them as we go from solid to liquid. So make sure we kind of understand what's happening, especially at these flat parts of the graphs where we are adding in energy, but we are not seeing a change in temperature. Oh, while I'm thinking about it, this is a really common misconception. The question will come up like, what happens to the temperature of water as it boils? So many students make the wrong choice of saying, well, as the water is boiling, the temperature is increasing. No, take a look at this chart. Temperature stays the same as it boils. If you've got a pot of boiling water and you put a thermometer in it, it is going to max out at 100 degrees Celsius if your thermometer is accurate. We can't get liquid water at 1 atmosphere of pressure any higher than 100 degrees Celsius. So don't fall into that trap. All right, the last graph that we're going to talk about today is a phase diagram. And phase diagrams look at the relationship between temperature and pressure. Most people kind of make the incorrect assumption that in order for something to freeze, temperature has to be really low. In order for something to boil, temperature has to be really high. Pressure plays a role with phase changes as well. We kind of saw that a little bit with the vapor pressure curves. Let's say you've got something at pressure A. We're changing in temperature from C to D. What phase change have we experienced? Well, based on our phase diagram, if we go from C to D, we have undergone melting. Temperature has stayed the same. Pressure has stayed the same. Temperature has changed, so the increase in temperature has caused us to melt. What if I stay at temperature C and I drop the pressure? I've gone from a solid to a gas. That represents sublimation. If I do the same thing at temperature D, again, drop the pressure from A to B, I've undergone boiling. So I can change phase simply by changing pressure. It doesn't just have to be temperature. I could go in the opposite direction if I wanted to. If I go from pressure B up to A, I can deposit the deposition. If I go in the opposite direction, I'd of course have freezing. and finally, condensation. Yeah, just a quick review of those phase changes. There's 2 points really to be aware of in this diagram. We've got the critical point. These are the conditions where it is impossible to condense a gas. Basically, the temperature has gotten so high at this point that no matter how much you push on the gas to try to force it together, it just won't happen. So you can't end up with a liquid beyond that temperature. Really interesting point, in my opinion, is the triple point. These are temperature and pressure conditions where we have all 3 phases of matter existing simultaneously. That might not sound all that interesting to you. You're like, I could have an ice cube sitting in a glass of water, and then I can have like water boiling, just on the stove across from where I'm sitting. Well, yeah, you could, but you've got different temperature and pressure conditions, or in particular, different temperature conditions for all of those. This is one set of temperature and pressure conditions at which all 3 phases of matter are present. This usually is only accomplished in the lab. I've got a short video showing you a triple point demo. So we're going to look at the triple point of tert butyl alcohol, which is a liquid at room temperature. And we use this thing called a standard vacuum setup. Basically what that means is we've got our sample inside this bell jar, and the bell jar is attached to a vacuum. Just like your vacuum at home kind of like sucks things up, a vacuum pump is going to suck air out of this bell jar. And as a result, we're going to see a decrease in pressure. The more the vacuum pump is on, it's just going to continue to suck air away from this closed system. Okay, so, they're zoomed in pretty close. We've got our tert butyl alcohol that's at room temperature. We're going to start to pull the vacuum. So as the pressure decreases, we're going to see boiling occur, even though the temperature hasn't changed. So this is boiling, and in theory, you could touch it, and it's still at about, 25 degrees Celsius, room temperature. It is not hot. The temperature has not changed. Just pressure has decreased, so boiling has occurred. We're going to keep evacuating that bell jar, keep pulling air out of this setup and decreasing the pressure. That boiling stopped. And see, about 2 minutes later, the triple point is going to occur. We keep dropping that pressure lower and lower and lower. And you can see over here, we're starting to freeze. So we're undergoing a phase change. So we are freezing, and as it is freezing, it's also starting to boil. We've got solid forming, or a liquid is present, and a gas is being produced, all under the same set of temperature and pressure conditions. It's really hard to kind of stop something at the triple point, but you can see it is freezing and boiling at the same time. That is pretty crazy. You do not see that normally. And eventually, it'll kind of go off the triple point, and we usually just end up in a single phase. But that is the triple point. I think it's a really cool set of conditions that we don't see often at all in regular life. It has to be in the lab. All right, chemists, practice with those charts and really being able to interpret your vapor pressure diagrams, heating cooling curve, and your phase diagram. Good job today. I hope you found this helpful, and thanks for tuning in.